Hello, phenomenal ladies and gentlemen. It's Matefaro here again, and welcome back to my space. This is another video in the playlist where we talk about the application of derivatives. And in this particular video, we'll be looking at an optimization problem. Optimization problems generally, there are questions in which we are looking for the largest value or the smallest value that a function can take. So there are different kinds of optimization problems. We have the extrema problem, where you look for the largest or the smallest value of a function in a particular interval or on the entire domain of a definition of the function. But in this other type of optimization problem, we are looking for the largest or smallest value of a function subject to some kind of constraint. And like I said in the related rate video, this is always a kind of problem for most students because it is a word problem. And many people struggle with word problem, which is why we are putting up this video so that we can see that it is actually not that bad to deal with. If you are patient enough, you can minimize your anxiety and nervousness and maximize your success with these kinds of problems. And you will realize that they are not intimidating as they look like. All right, so for general optimization problems like this case, the main thing you have to do is to read each problem slowly and carefully. Read it as much as you need to read it to really understand the problem. Sometimes the words can be ambiguous. That is the trick. Many examiners will try to put words together in a creative way, but it is important to know what the problem is exactly asking for. If you misread the problem or you hurry through, you have no chance of solving it correctly. So you take your time to read the wordings of the question, read the problem statement. If appropriate, if it applies to it, you draw or sketch a diagram of the problem. When you draw pictures, it helps you to organize your thoughts. It helps you sort out your thoughts. So you define the variables correctly and label your picture with these variables. It is very, very important. So, and for all optimization problems, there are always basically two types of equations that will pop up. We have the main function that we want to optimize, that will constitute the first equation, and the second one will be the constraint. So the constraint will always be some condition, so it will be described by an equation, and these are the two things that we'll put together to help us solve the problem. So the one equation is a constraint, the other is the one that we need to optimize. And the constraint equation is used to solve for one of the variables involved. There will always be more than one variable. So the constraint equation helps us to solve for one of the variables, which is then substituted into the optimization equation before we can now use the first derivative test to get the critical points and afterwards get the minimum or the maximum points. Without taking much of our time, let us dive into this question and see how all of these things come together. So let's read the question and understand what it's asking for. The question says a right triangle is placed in the first quadrant. So which is why I have provided a picture of the Cartesian plane here so that we understand where the triangle is. So this is the first quadrant of the Cartesian plane. So it means that we have a right angle triangle right in this quadrant. So the question says its legs are on the x and y axis. So when you have a right angle triangle, you to have two legs and the hypotenuse. The legs are the opposite and the hypotenuse. Well, we cannot talk about opposite and hypotenuse if there are no angles involved. So we just use the terms legs for the right angle triangle. But the hypotenuse is always the hypotenuse, whether there is an angle given to us or not. So in this case, we have two legs of the right angle triangle resting on the x and y axis. So it means we are going to look at something that looks like this. So given that the hypotenuse must pass through the point 2, 5, that is exactly a statement of the constraint. That is the constraint. Our hypotenuse will not just be any kind of line segment. It has to be the line segment that passes through 2, 5. That is going to be our constraint. We are going to see how that applies. Then, what are the dimensions and area of the smallest of such triangles? So it means what we want to optimize here is the area. So those two things. The first equation is the constraint equation that comes from the fact that the hypotenuse must pass through the point 2, 5, and the second equation is what we want to minimize, which is the area of the triangle. So let's get a more specific diagram. So we know that the triangle has the legs on the x and y axis. So we have two things like this. These are the legs of the triangle, and this is, of course, these are the vertices of the triangle. So we have 0, 0 here. So we don't know where this extends to, but let's just say we have a, 0, x is a, y is 0. And at this point, let's say we have 0, b. So the constraint is that the hypotenuse that I'm going to draw now must pass through the point 2, 5. So this is 2, then this is 1, 2, 3, 4, 5. This is 5. So that means I have the point here. So my hypotenuse must be something of this nature. So we have this right angle triangle that has the sides joining, the points joining 0, 0 and a, 0. That's one of the sides, which we can actually refer to as the base of the triangle. So we have a point here, and line joining them is the base of the triangle. And we have another point here, the 0, b, which we join by the second leg of the triangle. So let's put it this way. And finally, the hypotenuse, which there is a constraint on it that it has to pass through a point 2, 5. So there is going to be a point on here which is going to be 2, 5. So what we want to find is a minimization of the area of this triangle. And what is the area of a triangle? We know from elementary school that the area of a triangle is given by half times the base times the height. In this case, the base is the distance from here to here, and the distance from 0, 0 to a, 0 is just a. So maybe I shouldn't use, let me write it in full, times base times height. So in this case, the base is the distance between 0, 0 and a, 0, which is just a. And the distance between 0, 0 and 0, b is the height, which is just b. Okay, so the distance between, anytime you have the distance between a constant, comma, let's say x, or let's say p, and a constant and q, the distance between these 2 points is just usually the absolute value of q minus p. So absolute value because distance must be positive. Anytime one of the coordinates of your point is constant, the distance between the 2 points will be the difference between the non-constant components of the points. So instead of using the distance formula, square root of x1 minus x2 squared plus y1 minus y2 squared, we could just do that, and we'll get the same thing. So in this case, it means the area of this triangle which we want to minimize is half times a times b. So for the area, I'll make it f of, so this time around it is still f of a comma b, because we can see two variables here, half times a times b. For us to be able to use our first derivative test and second derivative test, we need to change it to a function of one variable, and that is where the constraint form equation comes in. So in this particular case, the constraint is that the hypotenuse must pass through the points 2, 5. There are two ways we can generate an equation from this condition. So one of the ways is to consider the fact that when we consider the slope generally. So the slope, since the point 2, 5, 0, b and a, 0 are on the same line, then the slope of the line joining 0, b and a, 0 will be the same as the slope between 2, 5 and a, 0, because three of them are on the same line. So what is the formula for slope? We remember that slope m is equal to y2 minus y1 over x2 minus x1. So we are saying the slope, so if I name this point capital A and name this point capital B, we are saying that the slope of AB must be equal to the slope of, so let me make this point P. The slope AP and also equal to the slope PB. But we only need two of them to generate what we need to generate. So what's the slope of, so that is the first method to get an equation for the constraint. The second one is to use the equation of the line. So we know that the equation of a line, okay, that could be in two cases as well. We could use the fact that the equation of a line is given by y x over a plus y over b equal to 1. This is the equation of a line where a is the x-intercept and b is the y-intercept. I'm using that because it is easy in this particular case. So because in our own diagram, the x-intercept is a and the y-intercept is just at point b. So we can use that equation of a line. You could also use the usual y equals to mx plus c, where the slope of this line, so the rise over run, is negative b over a. So that will be equal to, and c is the y-intercept. So that means that is negative b over a times x plus the b. So either of them will work. So let's generate an equation. So we'll see that both equations will be the same for the constraint. So using the slope, what the slope between the point A, so we want to say that the slope AB equals to the slope AP, where A is the point A, 0, B is the point 0, b, and P is the point on the constraint, which is 2, 5. So using the formula for the slope of AB would be, so this is x1, y1, x2, y2. So y2 minus y1, that will be b minus 0 over x2 minus x1, 0 minus a, is equal to, let us now use it for AP. So let's say this is our new x2, y2. So let me use prime there. So y2 minus y1, 5 minus 0 over x2 minus x1, 2 minus a. So with this we can get an equation. So this implies that b over negative a is equal to 5 over 2 minus a. Don't forget that what we are aiming at is to be able to make either a in terms of b or b in terms of a. Express a as an equation in terms of b, or b as an expression in terms of a. And this is easy from here, because we can immediately see that we can say that b is equal to 5a over a minus 2. So because when I multiply both sides by negative a, I get negative 5a over 2 minus a, but the negative can affect 2 minus a to become a minus 2. So that is the first method to get the constraint. The second method is to use the equation of the line. So we said the equation of the line is x over a plus y over b is equal to 1. So if this is the equation of the line, and we want the fact that 2, 5 is on the line, so it means 2, 5 will satisfy this equation. That means when we put x equals to 2 and y equals to 5, the equation will be satisfied. So we have 2 over a plus 5 over b equals to 1. And this means 5 over b is equal to 1 minus 2 over a. So that is 5 over b equal to a minus 2 over a. And this means that if I flip it on both sides, we're going to have b over 5 is equal to a over a minus 2, which implies that b equals to 5a over a minus 2. All right, so we have seen how to get the constraint equation on both sides, which means our equation, which was initially a function of two variables, 1 over 2 times a times b, can be made to be a function of a single variable. So when we substitute 5a over a minus 2 for b, we have this to be equal to this was ab. So half times a times 5a over a minus 2, which is equal to 5a squared over 2a minus 4. Now this is the area of the triangle that we want to minimize. So it is easy to find the minimum point and the minimum value of this function, since it is now in one variable. So we recall that to minimize or maximize a particular function, so the step is for us to find a critical point by solving the first derivative of the function that is equated to 0 for a. So when we solve f prime of a equal to 0, we get the critical point for a which is the critical point. So it is the critical point that is usually the candidate for the minimum point or the maximum point. If there is just one of them, then we know that it can only be either the minimum or the maximum. And if there are two of them, we can use the second derivative test to distinguish between them. So in this case, we have f of a equals to 5a squared over 5a minus 4. So to find the minimum point, we need to do f prime of a and set it equal to 0. So what is f prime of a? That is, we'll take the first derivative of this. This is a quotient. So where this is u and this is v. So we remember the quotient rule. The quotient rule, the y dx equals to v du dx minus u dv dx all over v squared. So in this case, v du dx, so v is 2a minus 4 times du dx. So maybe I should write things down. So u equals to 5a squared, v equals to 2a minus 4. So in this case, we cannot say du dx. So we can only say du dA. So the u dA here is 10a, and the v dA is 2. So it means f prime of a is v du dA, which is times 10a, minus u, which is 5a squared times 2, all over v squared, which will be 2a minus 4 squared. Now, this is the same thing as 10. I'm factoring out the 10 in the numerator. So this 10 and this 10. So we have 10 into bracket a 2a minus 4, then minus a squared all over 2a minus 4 squared. And this is exactly equal to 10 into bracket 2a squared minus 4a minus a squared all over, I can factor out 2 squared from the denominator. So we have 2 squared into bracket a minus 2 squared. It doesn't matter anyway, because this will just be 5 into bracket a squared minus 4a over 2 into bracket a minus 2 squared. So this is the first derivative that we are setting to 0. And when we want to solve for a fraction, a rational function equal to 0, what do? We just equate the numerator to 0. So this implies that 5 into bracket a squared minus 4a equals 0. And if we divide both sides by 5, we're left with a squared minus 4a, which is actually a into bracket a minus 4 equals to 0. So we have that either a equals to 0 or a equal to 4, that is a minus 4 equals to 0. But hold on, we are talking about a triangle where the base is what we have regarded as our a. So it means that a cannot be equal to 0. So which means a is equal to 4. So this is the base that will minimize the area of the triangle. We are certain that this is the minimum point, because if we put a equal to 0, we are going to get something that doesn't make sense, and b is going to be, so a equals to 4 is the minimum point in this case. So if a equals to 4, what is b? From what we have here, b equals to 5a minus 2. So we have b equals to 5a over a minus 2. That will be 5 times 4 over 4 minus 2, which is 20 over 2, which is 10. Therefore, the required dimension is for the base to be equal to 4 units and the height, so the leg 1 is 4 units and the second leg is 10 units, and the minimum area given by f of a for when a is 4. The formula for f of a is 5a squared. We could just use the half base times height. So our usual f of a comma b is the area, which is half times a times b. So at the minimum point, we know that our a is 4 and b is 10. So therefore, the area will be half times 4 times 10, which is equal to 20 square units. So the dimension of the triangle that would satisfy the constraints that will pass through, that the hypotenuse will pass through the point 2,5. The dimension is that the base has to be 4 units and the height has to be 10 units. You can figure out the hypotenuse using Pythagoras theorem, and you also find out that whatever you put, so this is 4, 0 and this is 0, 10. The equation of the line joining these two, which is the hypotenuse of this triangle, definitely contains the point 2,5, because that is x over 2 plus y over 10 equals to 1. So if you put 2,5 there, that will be 2. What is that? Sorry, a is 4. So x over 4 plus y over 10. So if you put 2,5, you have 2 over 4 plus 5 over 10, and that is 1 over 2 plus 1 over 2, which is equal to 1. So which means we are correct. So this video has already become longer than what I want it to be. So with that, we've come to the end of this particular question, and as you can see, it is a straightforward stuff. That just requires that you understand all the hidden parts of the question. You have to read the question to understand the problem statement, identify the variable or the equation you want to optimize. And when we say optimize, it could be to get the maximum value or to get the minimum value. Then we also have the constraint equation. In this case, it is the fact that the hypotenuse must pass through the point 2,5. So that will be all for this video. If there is anything that is not clear and you need more clarifications, and you can drop your comments in the comment section below. Otherwise, I see you in the next video with another application problem. Bye.